Hi everyone. In this video, I'm going to explain some basic concepts about logarithm by using this special graph reporting the number of coronavirus cases in different places. This graph is drawn based on what we call a logarithm scale. Right? So you can look at this vertical scale, which I will explain further very soon. We call this a logarithm scale because we make use of logarithm to produce this scale, this axis. And although you do not see logarithm directly, right? However, when you try to understand this graph and this scale, then you will better understand how the logarithm works. So what this graph really represents, this is actually telling you the number of coronavirus cases in different places according to the number of days since 100 cases reported in each place. And so the horizontal axis is the usual axis reporting the number of days, while the vertical axis is the reporting the total number of coronavirus cases. Okay. Now, if you look at the scale carefully, you will see that the numbers are not positioned in the normal way, like when we read normal number lines. Okay, and how it works. Let me explain or explore in details here. If you look at the starting point 100, okay, and you go up by this distance, you can see 1,000, and it is an increase of it is actually a relations, right, of multiples of 10. That means from 100 to 1,000, you expect 10 times, okay, change. And similarly, if you go up by the same distance, okay, on this axis, then you will see another 10 times, okay, increase from 1,000 to 10,000. In fact, if you put on any point on the scale, okay, the same distance, for example, here, represent from 2,000 to 20,000 is also a 10 times relation. And similarly, if you check this one, 500 to 5,000, it also represents 10 times, or a multiples of 10. So therefore, the actual distance on this vertical scale is used to represent ratio. Okay, so whenever you see a particular distance, no matter where you put it along this line, it always represents the same ratio between two numbers. Now, let's change a little bit. For example, if you start with 1,000 and look at the length leading to 5,000. This represent a multiples of 5, from 1,000 to 5,000. So if you put the same line here at the level 2,000, all right, will go up by the same distance. We'll need to exactly 5 times of 2,000. That means 10,000. So similarly, let's say if you go from 100 to 500, you will see the same length here again. Okay, maybe one more example. How about from 500 to 2,000? It will be a multiple of 4. Okay, so you can mark and check it again. It is also a multiple of 4. Okay, if you put it here. All right, so it will tell you once again the same distance. Now let's check another one. This one represents 2 times, from 1,000 to 2,000, which is a double. And then similarly, from 5,000 to 10,000 is also means a doubling, okay? And therefore, as I mentioned, whenever you see a particular distance, on this line, it always represents a particular ratio between two numbers. Now, but how is it useful? Go back to the graph itself again. This graph tells you the number of cases, how it is growing. Okay, and what's special about this pattern is that in most places, the number of cases seems to be growing along certain straight line in this graph. But what does it mean when they are lying on certain straight lines? Okay, now be careful. As I mentioned, the vertical scale is not the usual scale. Okay, and we'll see very soon that these types of points that are lying on the straight lines, in fact, represent a certain exponential growth. Now, why is it like this? Okay, let's go back to this graph again. So from let's say from 1,000 and 10,000 is an increase of 10 times. And if you take into account the horizontal scale, okay? So for example, if you go to the right right? In along this line, this horizontal line represents 5 days, okay, from 0 to 5 days. And if you go up in this way, then it means that in 5 days, the number of cases of coronavirus is increased to 10 times, right, of a particular value, okay? And so it is a very steep line on the graph, right? And unfortunately, we don't have any points lying on such line, but we may see that in, let's say, I can put it here, okay? Just to assume that this is a starting point, 5,000, and in 5 days, it goes up about 4 times, okay? Then it will be represented by this red line. And if you put it back to the graph, then you can see that many of these points are more or less on a line in this direction. And in fact, you can also see in the original graph this dotted line, right, showing 33% daily increase, right? So that means whenever you see some points, okay, seems to be changing, okay, by 4 times in 5 days, right, then it will also corresponding to actually a daily increase of 33%. Okay, and why is it 33%? Right? Maybe we do another calculation here to help us understand what it means. Okay, and let me put this way. Okay, so when we say increase of 33%, okay, that means we are going to multiply a value by 1 plus 33%, right? And so that is actually correspond to a factors of 1.33. But don't forget that if we are going to talk about 33% increase continuously, okay, let's say 2 days, then we should calculate 1.33 times 1.33, okay? So it will be effectively multiplied by 1.769, okay? And similarly, if you're talking about 33% increase in continuously in 5 days, then the factor, okay, leading to the growth should be effectively 1.33 to the power 5, okay? So which is more or less equal to 4. That's why we notice that this is more or less like an increase to 4 times the original value, okay, in 5 days. And so that's the reason why the dotted line here to help us to distinguish which parts of the graph, okay, the points or the numbers are growing more or less in this direction, right? That means corresponding to 33% daily, or that means go to about four times the total number in just 5 days, which is a quite varying situation actually. That's why at the beginning we keep track on these numbers and hoping that it will go down, okay, or not so rapidly. And so that's why in this graph, whenever you see points are lying on a straight line, it means that at that moment, okay, the points are more or less growing exponentially. Let's quickly see another case, okay? And for example, if you're looking at, okay, let's say doubling, okay, from 1,000 to 2,000, okay, but within 10 days, right? So then the graph will be something like this. The steepness will be something like this, and you can look at it here. For example, Japan. All right, now I put it here in this position, and in a certain period, okay, the number of cases in Japan is more or less like this. That means growing to 2 times or doubling in about 10 days. Okay, and so this graph, by looking at the steepness of the points on this graph, we can see quite clearly or easily when certain numbers are growing more or less exponentially, and particularly by how many times in certain number of days. And that exactly the usefulness of the logarithmic scale. Now, but go back to the basic question, then how do we decide where to put these numbers on the vertical scale, which are so strange to us? They are not positioned in a normal way, okay? Because the distance between them is not that uniform, right? Then how do we know where we can put down these numbers correctly on the number line? okay, to represent this kind of ratios. Now, I will explain it in another video later, in more details, okay? And this will show you the direct comparison between exponential graph and the linear graph. But before I end this video, maybe I can show you some quick demonstration to give you some basic ideas, okay, how the and how we can put the numbers, okay, on the logarithmic scale. Now, and the basic idea is like this, okay? If you look at, let's say, 100, it can be written as 10 to the power 2, that means 10 squared. Similarly, any numbers, in fact, can also be represented as a powers of 10. Now, you can use the logarithm to find the power. Okay, so I skip this part. So that means 200, if you check with your calculator and use the logarithm, then you see that 200 is 10 to the power 2.3. And similarly, 500 would be around 10 to the power 2.7. Okay, so this index or exponents can be found by using the logarithm keys in your calculator. It is exactly the meanings of logarithm actually. And one more example, okay, and then if it goes up to 1000, then 1000 is just 10 to the power 3. And now you can look at the index or the exponents here. All these all these numbers are written as powers of 10. And exactly, we are using this index to tell us where we should put the numbers 100, 200, 500, and so on a particular line. Okay, and okay, let's try to go on with this demonstration. So if I put it in the ruler, okay, something like this. Let's see. I start with a point here, right, and I take it as the index 2. Okay, and if I go up a little bit, 2.1, 2.2. Let's say this one is 2.3, 2.4, 2.5, 2.6, and then 2.7. Okay, I'm just reading in a normal way. 2.8, 2.9, and then finally 3. Okay, so these numbers, I'm putting the index, okay, in the normal way, just like a normal number line. Okay, and then, okay, now we can, on the left, okay, we can now position the number originally. So that means in the first place where you marked 2, which is the exponents 2, this represents the number 100. And then 2.3, right, here you will write down the number 200. So 200 on this scale will be positioned at this point 2.3. And similarly, 500, okay, put it at the point 2.7, and 1000, we put it in the point 3. Now, this number 100, 200, 500, 10, which is 1000, okay, it is just like in the original graph, how you see the numbers are positioned. Now, let's have a check about the ratio from 2 to 2.3. Okay, this distance of 0.3 represent a factors of 2, right, from 100 to 200. And similarly, the same length here, okay, also represent a factor of 2, 500 to 1000. Now, another example, if you look at the distance from 100 to 500, this is a factor of 5, okay, multiplied by a factor of 5. And similarly, from 200 to 1000, it is also represented by the same length, okay, 0.7, and also corresponding to a factor of 5, okay. And therefore, we are using the index, okay, to locate the point. And why it will work in this way, right? And you go back to think about it, when two numbers are in the same ratio, okay, and think about the index, okay, when they're represented as a power of 10, then the difference in the exponent should be the same. Okay, that is the basic properties about exponents. And in fact, this will be turned into an important properties about logarithm. So if you go on to learn more about the properties of logarithm. So this is the basic ideas about constructing or putting numbers in the logarithm scale. And so that we can reach graphs like this and help us to distinguish exponential growth in a more effective way. Okay. So if you're interested, maybe you can check my other video later to go on to explain more about the relation between exponential graph and the logarithm scale. Okay, thank you for watching this video.